I've given a general title, Atomic Scale Insights into Redox and Transport Mechanisms in Lithium Battery Materials. And my objective really is to give you an overview of some of the research in the group. So I'm going to start with any talk is really a menu. And with any menu, you have a starter. And the brief starter is a context slides about the materials and the modeling techniques that we use to explore these materials. The main course of this menu is to do with lithium-rich cathodes. I'm going to have a little bit of a TV break about an alternative battery. And then for dessert, we're going to move over to lithium-ion solid electrolytes, and I'll talk about their properties. So let's start off with the starter, the context, lithium battery materials. I think all of you are, in the electrochemistry space, you're familiar with the fact that lithium batteries have been highly successful. In fact, if you're watching this on a laptop or an iPad or even your iPhone, you know that they've really revolutionized these portable electronics. But the next challenge is the growth of electric vehicles. And there's been a massive growth. And in a way, the need for better battery materials has never been greater. And what we need for better battery materials, we need better advanced materials. We need to discover the discovery, the characterization, and the deeper understanding of these advanced materials. And then that links up with the applied side, the devices, cell assembly, manufacturing, and the lifetime and performance of these devices. And both of those areas are very much linked. So what is the battery research in the material space? It falls into different areas. In the positive electrode, the cathode space, a lot of research are looking at NMC type materials, nickel, manganese, cobalt, particularly nickel rich. Then there's an increasing interest in lithium iron phosphate, and an area that we're looking at, lithium rich compounds. On the negative electrode side, the anode side, there's work looking at obviously carbon composites, but looking at lithium metal and niobium oxides. Looking at the electrolyte, people are replacing the liquid electrolyte, the flammable liquid electrolyte, looking at all solid state batteries. And then beyond lithium, people are looking at sodium, potassium, and even divalent species like magnesium 2+. My research group largely is focused on lithium-rich compounds, solid-state materials, and sodium. But in this talk today, I'm just going to focus on lithium-rich cathodes and solid-state electrolytes. So I mentioned that we needed a greater atomic scale understanding. So when I go to parties, that's when I get invited, that is. When people ask me, Saiful, what do you do? Sometimes say I model. Obviously, I'm not modeling down the catwalk, but I am using very sophisticated materials modeling techniques. And there's a strong synergy with my experimental collaborators. So I'm showing you the yin and yang of modeling and experiment. So on the modeling side, we use density functional theory, molecular dynamics, but increasingly we're coupling the two using machine learning interatomic potentials. On the experimental side, people use synthesis, diffraction, spectroscopy, and electrochemistry, and a range of other experimental techniques like microscopy as well. But there's a strong synergy in my group between the two. For the non-modelers, let me remind you about the key modeling aims. Three main aims, I think, of modeling. One is, can we help to aid and interpret experimental data? The second aim is, can we get new insights that experiment might have difficulty, perhaps on the atomic and electronic scale? And then lastly, can we use modeling as a predictive screening technique? Probably the most challenging part of modeling. So what about modeling techniques themselves? I'm showing you here a plot of time scale along the y-axis and length scale along the x-axis. And you can see different techniques, ab initio, density functional theory, molecular dynamics, Monte Carlo, finite element, and continuum. And basically on the bottom left is the atomic structure. In the middle, we've got particles and grains. And right at the top right are devices. And I fall in the bottom left, very much the chemistry and materials side of things, where we try and understand the atomic and particle structure. But increasingly, we're using machine learning and AI tools to try and bridge the gap between ab initio and larger length scales. For example, we're using molecular dynamics techniques using machine learned interatomic potentials. And the advantage there is that we've got ab initio accuracy, DFT accuracy, but at a much larger scale. And I'll give you some examples later on in the talk. And if you want to find out more about some of the techniques we used, we've published a recent review in Nature Reviews Materials called Understanding Solid-State Battery Electrolytes Using Atomistic Modeling and Machine Learning, which goes into a bit more depth on the modeling side. And we were fortunate enough to get the cover image. So the cover image is on the right. So that's quite nice to get. And that was published August of last year. So let me start on the main course and start off on conventional cathodes, a couple of brief examples. So the conventional cathodes are based on two main materials. The first one is the layered oxide, lithium cobalt oxide, which has a redox process of 3+ and 4+ largely. And that material, in a way, dominates the portable devices that we use. There might be variations of cobalt oxide, but they are dominated. Below that is lithium-ion phosphate, which has an iron 2+, iron 3+ redox couple. And the structure is shown on the left, where you've got yellow octahedra, which are the iron octahedra, and the phosphate groups in blue. And that is the olivine structure. And both of those materials, the real pioneer behind that is John B. Goodenough. And he rightfully got the Nobel Prize back in 2019, but sadly passed away at the age of 101, actually. For those not sure, John Goodenough is the one on the left. The one on the right is a US president who actually believed in science, the truth, and the rule of law. Unlike somebody else we know. So we need a step change away from these conventional cathodes. So we need new materials and underpinning science. So let me give you some examples of modeling. We model the lithium cobalt oxide to look at the lithium diffusion properties. So those keen followers of solid state chemistry or material science will know the oxygens are in red, cobalts are in blue here, and you'll see that the green are the lithium ions. And what we can get out from these simulations are the diffusion coefficient for lithium, activation barriers from Arrhenius plots. But from these large scale MD, we can run up from 10 to maybe even 100 nanoseconds, which we can't do using conventional DFT techniques. So these are using classical and machine learned interatomic potentials. Another example is the lithium iron phosphate that I mentioned. This is a slice through the structure. The yellow polyhedra are the iron octahedra. The blues are the phosphate groups, and the greys are the lithium ions. And using computational techniques, we predicted that it was a 1D lithium ion conductor, but it was actually following a curved pathway. So that was a nice, clear prediction. That was a clear prediction that we published before experiment. And then with a group in Tokyo, led by Yamada and Yoshima, they did some beautiful diffraction studies and mapped out the pathway for lithium, shown in blue. That's the contour plot for the lithium pathway, again confirming that it was a 1D lithium ion conductor. But what was nice is that there was some nice quantitative agreement between our prediction and the contour plot from experiment. So that was some older work. What about new work? So we're looking now at lithium-rich layered oxides. And so let me give you some background to these lithium-rich materials. So what I'm showing you here is the potential up at the y-axis and the specific capacity in milliampere hours per gram along the x-axis. I'm showing you some conventional materials, lithium cobalt oxide and NMC, which reaches just over 200 milliampere hours a gram on the material side. And then lithium iron phosphate and the lithium nickel manganese spinel in green and purple respectively. But all these materials have a lithium to transition metal ratio of 1. The lithium rich materials have a higher ratio of greater than 1, but also a higher energy density. As you can see, in principle, the theoretical capacity can reach as high as 300 milliampere hours gram, so higher energy density. So this is a real scientific and commercial opportunity, but, and there's a big but, they present challenges. So let me introduce one of the exemplar or model systems. This is the lithium 1.2 manganese 0.802 manganese lithium rich cathode material. I'm showing you the structure on the top right, which shows the lithium in green. So it's a side view, and then the transition metal layer in blue. And you can see there are some lithiums in the transition metal layer, hence lithium rich. On the bottom right is some experimental data, some voltage capacity data, showing that there is a problem. There is some first cycle hysteresis, and there is some irreversible structural change. But also over many cycles, there is some voltage and capacity fade. So what's the advantage of these materials? Well, the advantage is the high energy density. There's no cobalt, there's no nickel, so we've got a much more sustainable material. But as I've said, there is voltage hysteresis and capacity fade. So the challenge is, can we understand what's going on at the atomic level? There is some atomic structural changes. Can we understand the nanostructural change? And what is the redox species in this material? So what is the consensus in these lithium-rich cathode issues? The consensus is that at the top of charge, there is structural change and oxygen release, or oxygen loss. There is anion redox, so oxygen is redox active. So what is the questions? What is the debate? The debate is, what is the structural change at the atomic scale, particularly at the top of charge? What is the oxygen redox species on charging? And what is the kinetically viable mechanism? So what is the debate? Well, the oxygen redox species could be, on the top left, could be localized holes or delocalized holes. On the top right, there is evidence that there is dimerization. So could it be superoxide or peroxide? Or on the bottom, could it be trapped molecular O2 in the bulk? And all of these have been proposed, and I'm going to show you evidence for particular oxygen redox species. There's also evidence from microscopy that there is some nanoscale void formation. So as you take out lithium, you're getting quite significant lithium cation vacancy clusters or nanovoids shown in this microscopy data here. But this presents a modeling challenge. There's a large degree of disorder. So there's a massive configurational space to search. So for those nanostructural changes, we've got to model large supercells greater than 10,000 atoms. So well beyond classical density functional theory, classical DFT simulation, We need to go beyond current techniques. So what do we do? So in my group, and this is led by a superb postdoc, Dr. Kit McColl, we've used two approaches. What I'm showing you is a schematic of our approach. So at charging, at the top of charge, we use two modeling strategies. To look at the kinetics, we use standard ab initio molecular dynamics, but for longer timescales. But look at the nanostructural and large-scale structural changes. To look at the thermodynamics of these changes, we use cluster expansion approach, which uses a large number of defect relaxations, more than 600. We do some structure mapping, we do some training, and then finally some lattice Monte Carlo of more than 50,000 atoms. And DFT can only look at typically 200 to 500 atoms, so orders of magnitude larger. So what do we find? What are our results? So what I'm showing you on the left is the starting structure of the top of charge. And then what I'm showing you in the middle there is the change in energy versus time in picoseconds. So obviously you expect the energy to begin to decrease as a function of time. And what we find, first of all, interestingly, we find some transient superoxide intermediates. So there's dimerization between the layers, but they're transient, they're metastable. And then at the end of the simulation, the thermodynamically stable is we find molecular O2 forms along these kinetically viable pathways. I stress kinetically viable pathways within these nanovoids, within these vacancy clusters. And remember, these vacancy clusters are quite large, so there is an internal surface of undercoordinated manganese. And that undercoordinated manganese leads to these unstable oxygens, which form these molecular O2. So the next thing we did is, what about the thermodynamics? That's kinetics. The thermodynamics. So again, I'm showing you on the left what's happening at the top of charge when we've taken out a large amount of lithium. 1.2 lithiums per form the unit. And this is using what I mentioned before, this cluster expansion approach and Monte Carlo, using more than 50,000 atoms. What we see is phase segregation into manganese-rich MnO2 and manganese-deficient nanovoids. And in those deficient nanovoids, we've got these molecular O2 in the bulk. But they're large, and they actually can be connected to the surface for surface release. So what's the experimental evidence for this? So there's, with my colleagues at Oxford, Peter Bruce and Rob House, they've done some oxygen K-edge resonant inelastic X-ray scattering, RIX. What I'm showing you is some data here for the pristine at the bottom, then the charge system. And you can see there's some signature which is not seen in the pristine. And those signature relates directly to gaseous O2, molecular O2, ties up very much with molecular O2. And then on discharge, we lose that signature and we form O2 minus again. And I stress on discharge, we're putting lithium back in, and that is stabilizing O2 minus species, but in different environments, and hence the hysteresis. So what is the take-home message? This was published in 2024 in Nature Materials. We call it phase segregation and nano-confined fluid O2 and lithium-rich oxide cathode. But what is the implications? The implications are we want to kinetically stabilize a pristine structure against, I stress, against structural changes and O2 formation. We do not want O2 formation if we want reversible high energy density lithium-rich cathodes. And related to this are disordered rock salts, which again are very topical materials. So a bit of background first. Again, they're lithium rich, so the ratio of lithium to transition metal is greater than 1. In this case, it's 2 to 1 for this oxyfluoride. And I think most of you are familiar with the rock salt structure, the stuff you sprinkle on your chips, on your rice or your pasta. In my case, before tequila shots. But anyway, I'm looking at this oxyfluoride, Li2MnO2F. It has a high energy density, 280 milliampere hours per gram, versus the classical lithium cobalt oxide. No cobalt or nickel, just pure manganese, so much more sustainable. And this is work we did within the Faraday Institution CATMAP project, Cathode Materials Project. So what do we find first from our calculations? So let me explain what I'm showing you here. What I'm showing you here up on the y-axis is the percentage contribution to the overall redox activity as a function of charge. So I'm showing you 1.75 lithium on the left and then 0.75 lithium on the right. So we're extracting 1 lithium per formula unit. So charging the material, lithium extraction. The blue is manganese redox and the red is oxygen redox. So you can see straight away on the left that at the start of charge, it's dominated by manganese redox. In fact, from simulations and Zane's X-ray absorption near-edge spectroscopy, the manganese redox is dominated by manganese 3+ and manganese 4+. We don't see any evidence of tetrahedral manganese 5+ or tetrahedral manganese 7+. And then as we increase the charge, we begin to see oxygen redox in red forming. But what's interesting is that there's some manganese oxygen redox overlap, which contrasts with the lithium-rich layered oxide. In the lithium-rich layered oxide, there isn't any overlap. And we think that's because in this disordered rock salt, we've got a variety of different coordinations throughout the structure because it's a disordered rock salt. And that's why you get more solid solution behavior and an overlap. So the redox overlap here is a range of manganese oxygen local environments in a disordered structure. So what happens kinetically? So here I'm going to show you snapshots from some ab initio MD at the top of charge from the starting structure on the top left and then the time evolution for our MD simulation. First of all, interestingly, we find manganese displacement first. That manganese displacement leads to some undercoordinated oxygen, and we begin to find some transient dimer species, for example, superoxide, and then right at the end, the thermodynamic product includes molecular O2 in the bulk and manganese, displaced manganese. So manganese migration and O2 formation, but short-lived intermediates of peroxide or superoxide intermediates, but they're short-lived. They are not the thermodynamic product. And then on discharge, when we put lithium back in, we're putting lithium into a very different structure because of the manganese migration, and that leads to a lower voltage and hence a voltage hysteresis on first cycle. And we published that a few years ago in Nature Comms on this disordered rock salt. So what is the take-home message here? The take-home message is similar. We need to suppress manganese migration and O2 formation if we want to harness high energy density lithium-rich disordered rock salts. And that has been done by people tuning the lithium manganese and oxygen fluoride composition, actually to inhibit oxygen redox in these materials. And if you want more details, it's published in Nature Comms back in September 2022. with that title. So what about, obviously molecular O2 in the bulk has been controversial. So I'm just following the evidence, our scientific evidence. We're finding from our very, very advanced simulations, RICS, we're finding bulk molecular O2. What about other techniques? This is work of Rob House using neutron diffraction PDF, pair distribution function analysis. And again, from the plot there, you can see that there are some features in the charged state not seen in the pristine. That 1.2 angstrom atom-atom pair is a signature for molecular O2. Nothing else has that short distance in the structure. This cathode was dried under vacuum, so the O2 is trapped in the bulk. We've also done some squid measurements, some magnetic measurements on a different material, a sodium manganese magnesium O2. And if you look at the magnetic data as a function of charge, shown on the bottom right, the actual magnetic data shown in blue, the blue dots, which is the Curie constant, it only ties up with molecular O2, triplet O2. The other oxygen species, dimer species, or oxygen O- species do not tie up with that magnetic data. Molecules in bulk solids are not unusual in other systems. If you look at the Nobel Prize winning metal organic frameworks, you get molecules in the pores, and in microporous materials such as zeolites, you get molecules in pores. So molecules in bulk solids is not unusual. So let me have a little break before we go to dessert. And for the last, I suppose, last 8 or 10 minutes, a short TV break. Abby mentioned that I gave the Royal Institution Christmas lectures on BBC TV. Most of you are probably not familiar. If you're not in the UK, you're not familiar with these Christmas lectures. They are tradition going back to 1825, where one of my scientific heroes, Michael Faraday, he's on the back of the old £20 note, started these Christmas lectures for the general public, particularly children. And on the left, you can see him giving that lecture within the famous Faraday Lecture Theatre. What's interesting, you can't see on the £20 note, but if you enlarged it, there are the famous terms that he helped to popularise: electrode, anode, ion and cathode. Anyway, they were first televised in 1936 on BBC, and some famous scientists are giving those lectures. David Attenborough, obviously on animals and particularly, and then one of my other scientific hero, Carl Sagan, gave them in 1977, and I saw them as a schoolboy. I was only about 14 at the time, so you can work out my age if you can do your maths correctly. Anyway, I was honoured, privileged, and very scared to give the 80th BBC TV anniversary lectures in 2016 on the theme of energy. They were the most stressful thing I've ever done, but this is the opening clip for those lectures on BBC TV. They were called supercharged fluid in the future, and obviously the theme was energy, and it was really a way of honouring Michael Faraday because it's the 80th anniversary. Anyway, one of the demonstrations, because it was very demo heavy, is how does a battery work? And I used a lemon. So when life gives you lemons, you make a lemon battery. And it's a classic school experiment. You can use a zinc nail and a copper coin in there, and you can generate a voltage if you connect it to a voltmeter. But I said to the Royal Institution, I don't want to use one lemon. In fact, I don't want to use a few lemons. I want to go large, very large. So we used 1008 lemons, cut them in half to get 2016 lemon slices, So this is true cutting edge technology. And we got a world record, 1,275 volts. In fact, the group said connecting those lemon slices wasn't the problem. It was actually making those IKEA shelves was the tough part. Anyway, I got a world record, a Guinness World Record. However, a group in Denmark broke my world record 2 years later. So I wasn't feeling sour or bitter about it, but I wanted a new zest for life to get that battery record back. And I did. 3 years ago, with the Royal Society of Chemistry, we used nearly 3,000 lemons to get a voltage of 2,304 volts. The current density, if you want to know, was tiny, and we've reused those lemons. Some of them for gin and tonics, but most of them they were used for biofuels by a company within the UK. Anyway, if you want more about it, if you go into YouTube and type 3,000 lemons, you'll see my video. Anyway, let's move on to dessert for the last 7 or 8 minutes. Solid electrolytes, nano-sizing effects. Some of you know that a big area is, can we move away from the conventional lithium-ion battery to all solid-state batteries? And the advantage there is could be safety, energy density if we use lithium metal as the anode, and there's a broader temperature range. But there are issues to do with conductivity, interfaces between the electrode and the electrolyte, and can we develop new materials? We wrote a review about the fundamentals of inorganic solid electrolytes in Nature Materials in 2019 with collaborators Theo and Christian at University of Picardie in France. And we got the cover image, which was nice. Not too different from the other cover image, but anyway, we got the cover image. So let me move on to the material we were interested in. This is the classic LGPS, lithium germanium thiophosphate. The reason why it's classic is in 2011, Kanu in Japan, in Tokyo, found that it was an exceptional fast lithium-ion conductor, 12 millisiemens per centimetre, which is really exceptional for a solid-state material. Low migration barriers, about, I think, 0.2 electron volts, and the bulk conduction mechanism was 1D. This is the structure on the right. It involves tetrahedral PS4 units and tetrahedral germanium S4 units with lithium in tetrahedral and octahedral sites. So it's a tetragonal structure. You can see it's elongated along the C-axis. But what's interesting in the last few years, there hasn't been any exploration of nanoscale effects. And we thought, oh, that'd be interesting from a fundamental point of view. So nanostructure solid electrolytes has been explored before. Why nanoscaling? We know that if you confine the dimensions to the nanoscale, we can get some very unusual properties. And this is in every field. If you think of any field, catalysis, magnetic, fuel cell, whatever field you're in, superconducting, if you nanoscale, you can get some unusual properties. There's been nanoscale of the Li3 thiophosphate. So these are two representative papers showing some high conductivity in nanoscaled materials, the lithium thiophosphate. But there hasn't been any effects of the LGPS, which is related to that lithium thiophosphate. So we thought we'd do some modeling work, some predictive work on this system. So what did we do? We did some large scale MD, nanoscale type modeling of 3 nanoparticle volumes. And we're doing large scale. We can't do this with DFT. Look at that, 100,000 ions we're modeling, and MD up to 10 nanoseconds, 10,000 picoseconds. So what do we find? So this is, it's always sad to represent lots of hours and hours of work. And this is work beautifully done by James Dawson, who's now on faculty at University of Newcastle in the UK. This is Arrhenius plots of different size materials. In blue is the bulk, and in red is the smallest nanoscale, as small as about 10 nanometers. And you can see the experimental data in black. So what am I trying to show? Well, I'm showing you, first of all, that there's reasonable accord, not perfect, but reasonable accord with experimental data, although the two experimental plots don't agree with each other, but we are in quantitative accord. But more importantly, the simulations predict that the conductivity would increase threefold by going down to the nanoscale. The calculated barrier is about 0.21 electron volts. The experimental bulk values range from 0.2 to 0.3 electron volts from impedance and NMR measurements. So the important result is the conductivity is enhanced by going down to the nanoscale. So that's a clear prediction. But this presents a challenge. The challenge we recognize is the synthesis of these nanoscale materials is not easy. And the other challenge is, what is going on? Why? What's the mechanism for this enhancement? So first of all, the structure. What's going on the local structural scale? What I'm showing you here is some radial distribution function, RDF, which is a bit like pair distribution function analysis from experiment. So on the left is the lithium radial distribution function. In green is the nano material, and in red is the bulk material. Very similar, but after the first peak, there's some broad peak suggesting quite a bit of disorder in the lithium-lithium sublattice, which is true. You're getting fast, liquid-like lithium-ion conduction for both bulk and nanoscale. In the middle there is the lithium sulfide RDF. Again, green is the nanocrystalline material, and in red is the bulk. A subtle difference is very similar, but the subtle difference, there's greater disorder for the nanocrystalline material. But what's interesting, this is the greatest one. If you look at the phosphorus, and even the germanium, the bulk material in red is quite ordered. However, the nanocrystalline shows incredible disorder, very different from the bulk material. So in short, the lithium-lithium shows disorder indicative of superionic conductor. However, the nanoscale, the tetrahedra are unchanged, but there's greater phosphorus and germanium disorder. But what does that look like? So this is the last results slide. I'm showing you, first of all, the bulk crystalline single crystal. On the top, I'm showing you the structure. The yellow is the PS4 and green is the GS4 tetrahedra. The blue shows the trajectory of the lithium ions from the trajectories of the MD. You can see it's largely along the C-axis, one-dimensional. And that's confirmed by the mean square displacement below the structure. The C shows the greatest diffusion in red, whereas the AB in green shows minimal diffusion, i.e. highly anisotropic, fast in the 1D. This was not new. I'm not saying this is new. This has been found before, for example, by Kanu a few years ago. What's new is what on the right. On the nanocrystalline, you can see straight away the structure is much, much more disordered, confirmed by the RDF. And the lithiums are moving in all directions, again confirmed by the mean square displacements. A, B, and C are completely identical in all directions, i.e. isotropic lithium-ion diffusion, 3D, fast in all directions. So this is the conclusion. The nanosizing enhances lithium-ion conductivity with a change in local structure, but also a change in the diffusion mechanism. So that's quite a nice prediction. And I recognise that there are some challenges of going down to the nanoscale. Just one slide on other work that we've done on solid electrolytes. This is a theme of the group, published just the end of last year. Some elegant work led by Wolfgang Zeyer in Munster, looking at the lithium-scandium halide lithium-ion conductor. And this was nice work of Ben Goldman and Kara Rosenbach, the two PhD students, looking at rotational stacking faults. And then a few years earlier, published in Nature Materials, some elegant work of Andrei Politeyev in collaboration with Aaron Lindenberg at Stanford, looking at the classical beta double prime aluminas, but finding out some fundamental defect-driven anomalous transport in those electrolytes. So if you want some details, go to those publications. So a quote really for the students in the audience, scientific outlook. This is a quote that I found at the Natural History Museum in commemoration of Charles Darwin. Despite my name, I am a devout humanist and Darwinist. And this quote, to me, speaks to me about science in general, but materials modelling in particular. And the quote is, "The real voyage of discovery consists not only in seeking new landscapes, but in having new eyes." And this quote is from Marcel Proust, the French writer and philosopher. So acknowledgements, just to conclude, obviously I have to thank the real people who do the great work. I think I learn as much from my students and postdocs as they learn from me. This is B, Kit, Chris, Luca, Felix, Arup, Becca, and Andre. The funders are EPSRC, Alastor, Faraday Institution, and Archer, the computational. And if you're interested in the work, here are some publications that you can take a photo of and delve deeper into those work. And finally, thank you for logging on and thank you for your attention. Thank you.